The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Good morning, everybody. I'm Wyslouch. I'm a teacher substitute for Professor Lee, who is now at some conference in China. And he asked me to talk to you about coupled oscillators. I understand that he introduced the concept last time. You worked through some examples. So what we are going to do today is to basically go through one or two examples of very straightforward coupled oscillators, where I will introduce various kind of systematic calculational techniques, how to set things up, how to prepare things for calculations. And also, we may, depending on how much time we have, start have driven coupled oscillators. And we will work on two, again, simple physical systems. One that consists of two pendula driven by forces of gravity, each of them, and then they are connected with a spring. So each of those pendula, each of those masses will feel the effects of gravity and effects of springs at the same time, and they will talk to each other. There will be coupling between them. So that's one physical example which we'll consider. The other physical example consists of two masses in a horizontal frictionless track connected by a set of springs. So they are driven by forces of spring. And those two systems are very similar to each other, almost identical in terms of calculations, and they exhibit the same phenomena, and I will be able to demonstrate several of the neat things. And this particular system is set up to introduce external driving force, which will create new set of phenomena. We'll talk about it today. And what I would like to stress today when we go through all those calculations is, A, how do you convert a given physical system with all the forces, etc., into some sort of fixed form, fixed type of notation with which you can treat all possible coupled oscillators. And also we will discuss various interesting, even though the system is very simple, just two masses, a spring, a little bit of gravity. On top of that, the way they behave could be extremely complex, but it can be understood in terms of very simple systematic way of looking things through normal modes and normal frequencies, etc., characteristic frequencies of the system. So let's set things up. So we'll start. This will be our workhorse. And by the way, once we understand two, we will then generalize to infinite number of oscillators, which is actually, so this model, which consists of weights hanging under influence of gravity plus the springs, will be then used for many applications of the concepts later in this course. So let's try to convert this physical system into a set of equations. So we have a mass m hanging from some sort of fixed support, another mass here, same mass for simplicity. We connect them with a string, and we know everything about the system. We know the length of each of those pendula, which is the same. We know masses. We know spring constant of a spring connecting those two things. The spring is initially at its rest position, such that when the two pendula are hanging vertically, the spring is relaxed. But if you move it away from verticality, the spring either compresses or stretches. And everything is in Earth's gravitational field, G. We assume that this is an ideal system, highly idealized. We only consider motion with small angular approximation, only small displacement. There's no drag force assumed. The spring is ideal, etc., etc. Of course, this thing here is very far from being ideal, but hopefully basic behaviors are similar. It's approximately ideal. To study the motion of this thing, to understand how it works, let's try to let's try to parameterize it and displace it from equilibrium and look at the forces and try to calculate equations of motion. So we will characterize the system by two position coordinates. We'll have x. We'll give this one number 1. This will be number 2. And we'll have x subscript 1, which in general would depend on time. This is a position of this mass with respect to its equilibrium position. We'll have x2 as a function of t. Again, this tells us everything. And the full description of the system is to know exactly what happens to x1 and x2 for all possible times. And we will impose some initial conditions. We can come back to that later. So the coordinate system is this. When we start talking about the system, in principle, in the case of somewhat larger angles, you have to worry about vertical positions as well. So we will introduce, so there's also a coordinate y, which we will need temporarily to set things up. So x is, as I say, x is measured from the equilibrium, y is positioned vertically. So to calculate equations of motion, we have to look at the forces. So let's look at what are the forces acting, for example, on this mass. The mass which is, if it's displaced from a vertical position. Let's say this mass 1, has moved by some distance away from the thing. Temporarily, let's introduce an angle here to characterize its displacement from vertical. And let's write down all the forces acting on this force diagram acting on this mass. So there's a tension in the string or the rod. Let's call it T1. There is a force of spring acting in a horizontal direction. This is a vector. And there is a force of gravity acting on this in the vertical direction. We can write down those forces. We know a lot about them. This one is minus mg y hat. This one is equal to k x2 minus x1 in the x hat direction. So this is the force which, when the spring is displaced from equilibrium, there is a spring force, hook force, in the direction of, in the usual direction, right? In this case, is actually in the opposite direction. And then there's a tension in the spring which has to be calculated such that we understand the acceleration of this object. So let's write down the equations in the x hat direction. This is m acceleration of object number 1 in x direction is equal to minus t1 sine theta 1 plus k x2 minus x1. And in the y hat direction, we have m y1 direction is equal to t cosine theta 1 minus mg. At small angle for theta 1 much, much smaller than 1, we can assume that cos theta 1 is approximately equal to 1, and sine theta 1 is equal to angle. We do the usual thing. So basically, in this approximation, and also by looking at the system, it's clear that the system does not move. The vertical direction can be ignored, yes? How do you know which way the spring force points? Excuse me? The force from the spring, how do you know which way it points? How do I know? Yeah. Do you just assign one or the other? No, the spring force is, well, you have to look at mass 1. We're just looking at mass 1. So the spring is connected to mass 1. And the force of the spring on mass 1 is k times however the spring is squashed or stretched. All right? So it knows about existence of mass 2, but only in a sense that you have to know the position of mass 2. So whatever, we just assume that x2 is something, and we just look where the spring is. So that's why the force of spring depends on the difference of position x1 minus x2. So it is written here. And in fact, interestingly, the position of the mass 1 itself, there's a negative sign here. So if you move mass 1, the spring force is in the right direction, minus kx. All right? So there is no motion x1, so we can conclude from here that t cosine 1 is approximately equal to 1. So t is simply equal to mg. So the tension in the spring can be assumed to be mg. We don't have to worry about it. And then we just plug in also the angle can be converted into position by realizing that the distance times the angle is equal to displacement, the usual geometry. Net result is that by simplifying things, I can write down equation for acceleration in the horizontal direction for mass 1 is equal to minus mg x1 over L plus k x2 minus x1. Okay? So this is an equation of motion for mass 1 in our coupled system. And most of the terms have to do with the motion of mass 1 itself, this is mass 1 as its own pendulum, and mass 1 as feeling the effect of the spring force. But because the force of the spring depends on the difference between positions, there is this coupling so the motion of mass 1 knows of where mass 2 is. And this motion of mass 2 influences the motion of mass 1. That's how the coupling shows up. So for most of those problems, what you do is you simply you focus on the mass in question. You take all the forces, you calculate them, and then this coupling will somehow appear in the equations. So we can repeat exactly the same calculation focusing on mass 2. And then the equation which you will get will be very similar. Let me just slightly rewrite this equation here to kind of combine all the terms which depend on the position of mass 1 with terms which depend on mass 2. So mx acceleration is equal to minus k plus mg over L times x1 plus k times x2. So this is the coupling term. So this is what makes those pendula coupled. All right, and then I can write almost exactly the same equation for mass 2 with the proper replacement of masses. So let me write this down in the following way. Kx1 minus k plus mg over L times x2. Okay, so this is, equation, the motion of mass x1 depends on x1 itself multiplied by something that has springy term and gravitational term, and depends on position of mass 2 only through the spring. Mass 2 also is mostly driven by its own gravitational force on itself, plus the spring, depends on position of x2. But there is this coupling term that depends on position of mass 1. So both of them feel the neighbor on the other side, right? So if I keep this one steady, of x2 equals 0, then basically the forces here is just the spring plus the gravity. If I move this one and keep this one at 0, force on this is spring and the gravity. But if this one is displaced and I move that guy, the forces on this one are affected by the fact that number 2 changed. Okay? Again, I was able to determine those coupling terms by simply looking at mass 1 itself, mass 2 itself. Right? So this is the set of two coupled equations I have accelerations here for x1 and x2, and I have positions here. So it's like in an oscillator, you have position acceleration with a constant term, except that things here are a little mixed. And the trick in this whole mathematics and calculations and the way we do things is how do you solve those coupled equations? Okay? So what I would like to do is, and there are, of course, multiple ways of doing that. So let me do everything. Let's write down everything in a matrix form, because it turns out that linear matrices are very useful for that. We will use them in a very simple way. So let's introduce a two-dimensional vector, which consists of x1 and x2. So basically, all the position x1 and x2 are here. So we will be monitoring the change of this x2 as a function of time. We will introduce a force matrix, okay, which is equal to k plus mg over L minus k here, minus k here, k plus mg over L there. This is a 2 by 2 matrix. And then we need a third matrix, mass matrix, which simply says that masses are, mass of first object is m, and the other one is also m, right? So these are the three matrices that basically contains exactly the same information as out there. I probably need another matrix. I need inverse matrix for mass, which basically is 1 over m, 0, and 0. This is an inverted matrix. Okay, and it turns out that after I introduce these matrices, this set of equation can be written simply as x, the second derivative of the vector capital X, is equal to minus m to the minus 1, which is this matrix, multiplying matrix K, and then multiplying vectors X again. All right? So this is exactly the same as this, just written a different way. So it's only the question of notation. So it turns out it's very convenient to use matrix calculation to do things faster. So instead of writing all the x1s, x2, et cetera, I just stick them into one 2-element object. I use matrices to multiply things. And if I want to know x1 and x2, I can always go, OK, the top component of vector x, lower component of vector x gives me the solution. Simple, right? So let's try to use this terminology to find solutions. So the question is, how do we find solutions to coupled oscillations? What is the most efficient way of finding the most general motion of a coupled system? Anybody knows? What's the first thing? Yes? Introduce what?
Coupled excitation. Using coupled excitation.
Coupled complex excitation. Yes, that's right. So I can, all right, let's do it. But hold on, but what form of oscillation? Okay, there are all kinds of complex numbers you can write, but any particular? That's the thing. That's the physics answer. All right. Complex notation is a mathematical answer, how to solve mathematical equation. But the physics answer is to find fixed frequency modes such that the system, the complete system, oscillates at one frequency. Everybody moves together. This is so-called normal mode. It turns out that every of the system, depending on number of dimensions, will have certain number of of frequencies, normal modes, that the whole system oscillates at the same frequency. Both x1 and x2 undergoing motion of the same frequency. We don't know what the frequency is. We don't know its amplitude, etc., but it is the same. Okay? So this means that I can write that the whole vector x, both x1 and x2, are undergoing the same oscillatory motion. So I propose that, so of course we use the usual trick that anytime we have a solution in complex variables, we can always get back to real things by taking a real part. So we've done this. I understand you've done this before. So let's introduce a variable z, which is kind of two-element vector, which has a complex term, a fixed frequency plus a phase, everything complex, multiplying vector a fixed vector A. Okay? And vector A is it simply has two components, A1, A2, or maybe I should write it differently. So vector A contains information about some sort of initial conditions for position x and 2. Anyway, these are two constant numbers. And also we will, because we have this phase here, because we keep phase in this expression, we can assume and require that A is a real number. So A is real. It's slightly different ways of doing things, but we can assume this for now, right? So the solution which is written here, it's some two numbers, oscillatory term, where both x1 and x2 are oscillating with the same frequency, and this is our postulated solution. So we plug it into equation, and we adjust things until it fits. So let's plug this into our matrix calculation. And what you see here is that, so what do we have? So we have so this is the term which is second time derivative of vector x. And because vector z, really, so I have to do, so I plug this here, so z double dot is simply equal minus omega squared times z. Right? I write it like this. So this is a simple thing. When I plug this in here, my equation becomes equation for A. Because so I take this, so I have minus omega squared z hat, which maybe I just write it immediately in terms of a complex term by times the vector A. So I have e to I omega t plus phi times A is equal to minus m to the minus 1k times e to the I omega t plus phi times vector A. Okay? And this term is it's a proportionality constant at any given moment of time, so it goes through the matrix multiplication very easily. So you can just delete this, you can divide both sides. You have signs here, and then I have equation which it's a matrix, linear matrix equation, which is m minus 1k times vector A. And I can rewrite it a little bit again. So I can rewrite in this minus 1k minus omega squared times unity matrix times vector A is equal to 0. So this is the equation which we need to solve to obtain the solutions to at least one normal mode. And we expect that there will be two normal modes because we have two masses. Okay? So now, this is, so this is some matrix, 2 by 2 matrix, which we can know very easily how to write. Multiplying a vector gives you 0. It turns out that for this to work, there are two, there's a criterion which has to be satisfied, namely the determinant of this 2 by 2 matrix has to be equal to 0. Because if you take determinant of both sides, you have to have 0 on this side to be able to obtain 0 on the other side. So mathematically, the way to find out the oscillating frequency is you take a determinant of m minus 1 k minus I omega squared must be equal to 0. So let's try to see how to calculate things. So let's write down this matrix explicitly using this and that. So let's write this down. So I take a big object like this. And so in this element here, I have to multiply this matrix times that. If I multiply this matrix, I simply divide all those. Effectively, multiplication of m minus 1 times this matrix divides all the elements here by m. That's all there is to it. I just divide everything by m. So I have so the first m minus 1k is k over m plus g over L. This is minus k over m minus k over m, k over m plus g over L. So this is multiplication. This is this term here. And then I have to do minus unity matrix times omega squared. All this will do is it will subtract omega squared here. And maybe I should rewrite this. Okay? So this is on this one. Maybe it would be more clear if I move it over here. All right, so this is the matrix that contains all the information about our system, the mass, the gravitational acceleration, the length, the spring strength, etc. And we assumed that it oscillates with a fixed frequency. So I have to find a determinant of this matrix equal to 0. Okay? So how do I get that? And by the way, okay, you have a matrix and you want to make sure that its determinant is 0. It turns out the only variable which we have to change parameters of this matrix, the spring constant and the masses are fixed, is given. The system has been built. It's hanging over there. I cannot change anything. So the only parameter here which I can change or adjust or find is omega squared. So I will try all possible matrices of this type until I find one or two that have a determinant equal 0. And if I find them, this would correspond to the normal frequencies. Okay? So how do I calculate determinant of a 2 by 2 matrix? I do this by this minus this by that, right? So that of this matrix is equal to k over m minus g plus g over L minus omega squared. There are two identical terms, so I can put a square, and then minus this minus k squared over m squared must be equal to 0. Right? So this is the equation which we need to solve. We need to find which parameter omega sets this to 0. Okay? And then, this is a pretty straightforward calculation, except that I don't necessarily have. Let me just use this one. Okay, so let's rewrite this a little bit. So this is basically equivalent to the following equation: G over L plus K over M minus omega squared must be equal either to plus or minus K over M, right? I took a square root of both sides. If you take a square root, you have to worry about plus or minus signs, right? So, so there are two solutions, which corresponds to plus here, the other which corresponds to minus here. So solution number one, which corresponds to plus sign right here, it basically says that omega squared is equal to G over L. Right? So there is one solution, one oscillation that does not depend on the spring constant because spring constant cancels. And there's a second solution which corresponds to minus, where omega squared is equal to G over L plus 2K over M. Right? And that's it, because there are two possible solutions, and this is what we have. So we have so what this says is that if I set my frequency to G over L, if I set the system to oscillate at this frequency, then it will be, I will be able to set things up such that it oscillates forever at this frequency, one fixed frequency forever. And this is interesting. This is a frequency that does not depend on the strength of the spring. How is it possible? Somehow spring is irrelevant for this motion. And it turns out that there is a very simple oscillation, easy to see. If basically this is a frequency of a single pendulum. So basically you get both pendula going together, each of them happily oscillating by themselves, and the spring is completely irrelevant for this motion, right? If I cut it off, the motion will not change. It just happens that two identical pendula are going at their own natural frequency. So the force of spring is irrelevant, nothing happens, this is a normal mode. And it can go forever at this particular frequency. Okay? The other option is, it's usually symmetrically, I move them away from each other, and this is the motion where, again, this is not exactly ideal small angle oscillation, but yeah, let me try again, maybe it's somewhat less. So this is the situation where the spring really comes in at full force. It's being stretched maximally because they go away from each other, so very quickly spring is stretched, and then go together, so it's stretched from both sides. And the whole system oscillates at the same frequency, and because of this additional force of spring, the frequency is actually higher, it's larger. It oscillates faster. All right, so that's the first step in understanding the system. We now know that there are two oscillations and two normal frequencies. And the next step to finish our understanding of the system in a mathematical way, to describe it fully, I have to know what is the shape of oscillations. I simply showed you here, so you know what to expect, but I have to be able to dig it out from the equations. And the way to dig it out is to find vector A. See, our real equation of motion is up here. This is equation of motion. This is, I have to now find the vector A, which, when you plug it in, it works, it satisfies this equation. So I already know what are the two possible omegas that can do it, but still I have to find vector A. So I have to solve two separate independent problems. One is find vector A for this situation, and then find vector A for that situation and see it works. So I have to plug in the whole, I have to plug it into the whole equation. And you can show that if you set omega squared to G over L, and you plug it into, if you plug it into this equation, what you get is a matrix equation which looks like this: K over M minus K over M minus K over M, K over M. And this is because try to hit it. So if you plug omega squared here equal to G over L, then this cancels out, and this cancels out. So you plug it in here, and you get this very simple matrix that has only K over M terms. So the question is, what sort of thing can you put here to get 0? What kind of vector you can plug into those two places such that the matrix times vector will end up with 0? And one example is that basically amplitude is the same. Both of them move together. So you plug one here and one here. Right? So this is a good solution. And every other solution is a linear multiplication of this one for this frequency, right? This K over M times 1 minus K over M gives you 0. So this is a good solution for, so this is solution number 1. What about this thing here? If I plug this omega squared to into this matrix, it's G over L plus 2K over M. If I plug it in here, then this matrix is a bit more complicated. It will actually look very similar, but with important differences. So this one will look minus K over M, minus K over M, minus K over M, minus K over M. OK? And then again, for this second possible normal frequency, I have to find the vector A, which corresponds to that frequency motion. And it turns out that they are the same, but the sign changes. So one possible solution is minus 1, and minus 1. If I plug in 1 and minus 1, then this matrix times the vector gives you automatically 0. So this is the second possible normal mode. All right? So this is a systematic way to solve equations. You plug in all the information you know about the system into a 2-by-2 matrix, and then you calculate the normal mode, and then you calculate a shape of a normal mode. Is that clear? Any questions at this stage? All right? So in principle, we know. Now, at the end of the day, I still want to know how mass 1 moves, how mass 2 moves. So we have to put it all together. We have identified the frequency and the kind of, in the matrix notation, shape of the node. But of course, the final solution is a linear superposition of all possible normal modes with, describe, position of mass 1, position of mass 2, etc. So let's do a little bit of, so maybe graphically I can write down that this is the oscillation that corresponds to this type of mode, that those two masses move together. And this is oscillation that corresponds to a mode where masses move in opposite directions. At any moment of time, in this normal mode, at any moment of time, wherever mass 1 is, mass 2 is minus the distance away from its own equilibrium. So if this one is plus 1 centimeter here, the other one is minus 1 centimeter. This one is minus 5, this one is plus 5, and so on. Whereas in this mode, both of them move together. All right, so let's try to go back to we can get rid of this one. Let's try to go back, and now with this knowledge, let's write down x1 and x2 for positions of the two masses. So basically x1, so basically, the x will have to be, I used z there, so x will be real of vector z. So I take my complex numbers, I take a real of them. So from exponent, I will end up with a cosine appropriately and so on. And then I will use the amplitude. So this is real part of e to the I omega plus phi, where omega is one of the two possibilities, omega t plus phi times vector A, which we've identified here, and times some additional. These are those vectors A. This is one possible amplitude of notation, but in general, it can be anything. You can multiply. You can have a small oscillations, large oscillations. So there is some overall amplitude, but the shape always have to be the same. They either go together or they go opposite. So to make it more general, I have to give some multiplicative factor there. So if I do everything, I end up with x, the mode 1, will in general have some sort of overall constant c, cosine omega 1 t plus phi 1 times this vector 1, 1. This will be for x1, this will be for x2. And the mode number 2 will be c2 cosine omega 2 times t plus phi 2 times 1 minus 1. All right? So let's see what things are adjustable and what things are fixed. So the omega 1 and omega 2 are fixed, given by the construction of the two coupled oscillators. This shape 1 and 1 and 1 minus 1 is fixed, because these are the shapes of normal modes, which correspond to those frequencies. So we have only 4 constants. Overall amplitude C1 for normal mode 1, overall amplitude C2 for normal mode 2, and then relative phase of those two normal modes. And the superposition of x1 plus x2 gives you the most general combination of possible motion. So if I write this down now in terms of position of number 1, number 2, so I have position of x1 as a function of time. In general, will look like this. Will be some sort of constant alpha, cosine omega 1 t plus phi, plus constant beta, cosine omega 2 times t plus phi 2, phi 1. So mass number 1, this is position of mass 1, will in general be a superposition of the two possible oscillations. Position of mass 2 will be very similar, but there will be very important difference between them. It will be alpha cosine omega 1 t plus phi 1 minus beta cosine omega 2 t plus phi 2. This is very important to understand exactly how this equation came about. You see, this is the influence of the symmetric mode, where the two things are together. So they are multiplied by alpha, some sort of arbitrary amplitude constant, but with exactly the same sign. And this is part which corresponds to a second mode, which is with different frequencies, and there's an opposite sign between this amplitude and that amplitude. So you have only four coefficients, alpha, beta, phi 1, and phi 2, which are determined, which need initial conditions. So any arbitrary mode, this is the most general motion of the two coupled oscillator systems. And to describe it specifically, to find for a specific configuration, you will have to determine values of alphas and phis. Okay? So what I want to do is I want to write down a specific motion for the following situation. So I keep position of x1 at 0. It's not moving, so its velocity is 0. I displaced this one by small positive amount. So the position of number 2 at t equals 0 is different than 0. It's some displacement x0 or something. And its velocity is 0. And then I let it go. Okay, again, this is not the ideal coupled oscillator, right? Okay, but this is, and then you see that things start moving together. Let me try to show it again, because it's not exactly obvious. So this one will be going on. So let's say this one, it's running, and then I let this one go. And what you see here is that, this one is moving, and then that starts to move. This one stops. That starts moving. It starts being complicated, right? It's a kind of complicated motion. But whatever this motion is, we know that it's simply those cosines which are kind of adding up to give you this impression of relatively complicated motion, right? So again, I let this one out. Okay, let it go. This is my T0. See, this one slows down. This starts going. And this one then slows down. The other one starts going. They kind of talk to each other. And it's this combination of cosines. All right, so let's try to simplify this for a specific case of a specific initial conditions. So if I set, so I set x1 equals 0, at t equals 0, x1 velocity at 0 is equal to 0. So these ones are not moving. x2 at 0 is equal to some sort of x0, and x2 velocity at 0 is equal to 0. So this one is displaced. They're all stationary. This one is at position 0. If I plug this in, it turns out, without lots of details, that what you will get is that alpha will be equal to x0 divided by 2. Beta will be equal to minus x0 divided by 2. And phi1 will be equal to phi2 equal to 0. You can check if you plug it into those equations. If you plug t equals 0, phi is equal to 0, etc. You will see that it works. So you can write down the specific case of x1 of t to be x0 over 2 cosine omega 1t minus cosine omega 2t. It's because beta has a negative sign. And x2 of t will be equal to x0 over 2 cosine omega 1t plus cosine omega 2t. Okay? So each of those objects effectively feels the effects of omega 1 and omega 2, but in a slightly different way. That's why their relative motions are different. So what I will do now is I will show you an animation. Hopefully it works. And we will have time. Since on the computer you can make things perfect, let's do it. So I'll have running a MATLAB simulation. Let's see how it goes. Let's make it large. So what is going on here is the following. I took some initial condition. I'm not sure if exactly the same, because this was for the course that I taught some time ago. What you see here is the following. You have the green is the normal mode number 1. The red, no, the magenta is normal mode number 2. And blue and red are the actual pendula. All right? And the motion of blue and red is simply a linear sum of the two. And what you see here is, and then I plot the position of the blue and red in color as a function of time. So you see this weird effect that, let's say, red now stopped, and the blue is at maximum, and now the red is picking up, and now the blue stopped, and the red is going full swing, etc. And this is exactly what, this is the computer simulation that shows you that one of them is going up, the other one down, etc. And this is for the certain combination of initial conditions. I could go, change initial conditions in my program and have a different behavior. But whatever happens, I would be able to, it will always be a combination of the two motions. Now, is there a way to disable one of the normal modes? How would you disable one of the normal modes? Is there a way quickly to set things up such that the second normal mode, whichever you choose, doesn't show up in the equations at all?
You only let it oscillate as the first one, so you set the initial conditions so that x1 equals negative x2.
For example, yeah. So what you do is you just change initial conditions. So you set it up at t equals 0. I have initial conditions that basically favor or demand that only that in this general equation, either alpha or beta is equal to 0. So for example, I can, one possibility is I move both of them at the same distance, and I just let them go like this, such that the spring is irrelevant, right? How would I do it in my software, in my program? I don't know. I can, for example, set one of the initial conditions to. No, this is still running. The old one is still running. Okay, so this is just a moment. So what I did is I just changed initial condition. And you see this is the type of motion where one of the modes is stopped, just we switched it off, and the other one is going on, and then of course the total motion is equal to that, and both of them happily go with a constant amplitude. There is no shifting of energy from one to another. So you can have all kinds of motions by simply adjusting initial conditions, and those motions can be done a very different way. Now, so do you know? So this is how we can have different shape of motion depending on the initial condition. Is there another way for me to change the way this system behaves? Let's say I have exactly this system, and I want to change, for example, the frequency of oscillations. How would I do it? It could be a very expensive proposition, yes? Yes, but I don't want to drive it yet. I just want to have it, a free oscillation, yes? Yeah, I could come and scratch it away a little bit, and yes, the equations depend on the mass. No, but I don't want to touch. I want to just have this thing. I don't want to make any physical modification to this system. However, I can move it into different places. Any place you can think of where I could really modify the oscillation. Yeah? To the moon, exactly. I could put it with me, some spaceship, and go to a place where gravity is different. Right? Why not? Okay, so what would happen? So if gravity changes, then basically what will happen is both this term and that term will change. The spring will remain the same, mass will remain the same. So the relative magnitude of omega 1 and omega 2 will change. Okay? So let's say, in fact, do I have it in this one here? Yes. So let's say I do again. So this is what I had before. Right? So this is the one here, which is operating here on Earth, and I let it go. I displaced it by a certain distance, let's say 1 millimeter, and that's how it's going. So now let's take it to, for example, Jupiter. So what do you think will happen when we go to Jupiter? Jupiter, G is much larger. Okay? So what would happen to those? So the frequency will be larger. Thing will be faster, right? That's the higher frequency. But also the difference between two frequencies will be smaller. Okay? And what happens when the difference between frequencies is smaller? You saw this effect that the energy was moving from one to the other. Do you think it would take, so one of them was oscillating, the other one was stationary, then the other one would pick up, etc. Do you think this transfer of energy will be faster or slower? 2 omegas are closer to each other. Any guesses? Slower. Slower. It will take kind of longer. Let's see what happens, right? So we go on a rocket, and see, nowadays you don't have to go to a rocket, you just remove one comment. And I went from about 10 meters per square second to 25 meters per square second, and this is what is happening. Look at this. So first of all, this identical system, everything is the same, time is the same, and so on. So you see that oscillations are much faster. So number of amplitude changes per second is larger, but it takes much longer for the energy. So the red one is now stopping, and you see now slowly is coming up. So because the 2 frequencies are closer to each other, they stay, it takes longer for them to shift from one to the other. Okay? So we are done at Jupiter. Let's now go to the moon, which has much lower gravitational acceleration. Let's see what happens. Again, by logical argument, so the smaller gravitational accelerations means that the frequency is now lower, so the pendula will move slower. However, the difference between frequency will be larger because the spring is still the same strength. So it turns out that even though everything is slower, but the energy transfer will actually be faster. So let's try to see what happens on the moon. It's okay. It's a little bit not completely clear what's going on, but you see, actually the motion is kind of a little strange. Look at the red one. The red one is stopping, then it's going halfway out. It looks kind of messy, doesn't it? And so it doesn't show up here very well because the parameters have changed so much. So I have those some sort of fixed pictures, which are okay. Just a second, I'll show you. So this is the show. Okay. So this is the picture on the some sort of stationary picture on the Earth. I saw one of them up, the other one down. You see that them shift from one to the other, and you can see kind of frequency of how the energy shifts from one to the other, and also you can see the frequency going up and down. For the same exactly conditions, this is now, just a moment, this is at Jupiter. So at Jupiter, you see that the frequency itself is much higher, and the energy transfer between the two things takes longer. And on the moon, however, the oscillations actually look really weird. This is an example of one of them. It's kind of, the 2 frequencies are so far away, and that it's really not even a nice oscillatory motion. Some sort of, it's much less obvious that this is a superposition of 2 cosines because they're kind of exactly out of phase, etc. So the motion is kind of complicated. Anyway, so this is the lesson is that the exact shape, the exact motion, we know that it can always be decomposed into simple motions. If you put them together, things may get really interesting and complicated depending on what sort of frequencies we are running and what sort of initial conditions we have. All right. Yes, any questions? Yes.
Are these graphs talking about the center of mass of the system, or like just one of the 2?
This one, I think, this one is just one of them. Actually, the one of the difference, it almost doesn't matter. What matters is the frequency and how they move to the other. Okay. All right, let's just forget about it. Just keep it. So let me now talk about this thing, which is called beat phenomenon. Because when you look at the motion of one of those objects or the difference between them, or whatever. There's something kind of interesting which can be extracted for those equations. Let's look at these equations here. Let's look at mass 1. This is mass 1, mass 2. So I can rewrite those solutions in a little bit different way. And so what I want to do is I want to, you see, this is a difference of two cosines. This is a sum of two cosines. There are lots of neat trigonometrical identities which we can use. So we do zero physics. Here we just rewrite the trigonometrical formulas. So I do exactly this, but I rewrite it. I use, for example, you have a cosine alpha plus cosine beta is equal to 2 cosine, is equal to 2 cosine alpha plus beta divided by 2 multiplied by cosine alpha minus beta divided by 2. Right? That's the trigonometric identity. Right? So let's just use this to write this down. And what you get is x1 of t is equal to minus x0 sine of omega 1 plus omega 2 divided by 2 times sine omega 1 minus omega 2 divided by 2 times t. And x2 t is equal to x0, some amplitude, cosine omega 1 plus omega 2 divided by 2 cosine omega 1 minus omega 2 divided by t. So again, we did zero physics here. We just rewrote the simple trigonometric equations. But what you see is something interesting here. So there is we have those two frequencies which are playing a role. And for example, at Jupiter, those two frequencies are actually very close to each other because everything is dominated by the gravity, and we have very weak spring. So the omega 1 and omega 2 are actually very close to each other. So this term here, kind of goes omega 1 plus omega 2 divided by 2 is like omega, right? 100 plus 105 divided by 2 is about 100. Whereas this one here carries information about the difference of frequencies. 100, 102, the difference is 2, which is very small. So how would this look like? So if you make a plot under some conditions, you can, let's say, so the two frequencies are close to each other. So if omega 1 is close to omega 2, for example, omega 1 is 0.9 times omega 2, right? This is roughly what we have on Earth in case of our system here. Then omega 1 plus omega 2 divided by 2 will be about 0.95 omega 1, omega 2, I think, which is approximately equal to omega 2, omega 1. And omega 1 minus omega 2 divided by 2 will be about minus 0.05 times omega 2, much, much smaller than that. How can we see? So we have so this term here, it basically oscillates at the frequency of omega, of frequency of individual pendulum. And the other term is much, much smaller. How does this look? Well, it turns out that if you make a sketch of this, if you do a sines, for example, it looks like this. Okay? So there are, in fact, when you look at this picture, you can see two frequencies. One, which is clearly this oscillation of the high frequency oscillation of things moving up and down. But there's also this kind of overarching frequency of much smaller frequency. And this is what corresponds to a difference of two things. So in a sense, you have, if you look at this formula here, you have oscillation which is happening very quickly with a typical oscillation of the system. But this is like a modulation of the amplitude. So the amplitude of the signal is changing. And this is what you see here. This is exactly the picture out there. So you have so the system oscillates. So one of those pendula, either of them, is moving fast, but it's going faster. Its amplitude is larger, and after some time, it slows down to 0. Goes higher and slows down to 0. And you've seen this. We can do it again here, that both of them oscillate at roughly the same frequency, but their individual amplitudes are changing. And this transmission of, one of them moving full blast, the other one moving full blast, there's this kind of frequency of energy moving from one to the other, which is something called beat. This is a beat system, beat phenomenon, somehow that energy is moving from one place to another. And we can have some demonstration of how this happens. So we see this here. We see it on the pendula. We saw it on a computer simulation. But now what we are going to do is we are going to try to hear it. All right? So this is the demonstration, which maybe it works, maybe not. So let me, it will work, okay? So let me explain what we have. So we have two speakers, and they basically go on very, very similar frequencies. All right? So they both work at similar frequencies. And so when I switch them on, you should hear the sound. Okay? So this is the frequency. I believe it's just one of them is working. And, this is just one pendulum that is going on the given frequencies, right? Then I'll switch a second loudspeaker. No, my friends. These are not these. This is Prof system. Okay. Can you hear this kind of wiggle? I'm changing frequency one of them. Oh, this is normal. Right? This is not the frequency of the original sound, but it's kind of the loudness of the sound overall is changing. Right? This is faster. This kind of extra sound which you hear, it's the difference of magnitude. The frequency is not stable here, so it changes. Right? So this is a single one. Perfectly constant frequency, no change in amplitude, no change in loudness. Put them together, right? That's what they do. So if you have two, and I can adjust the frequency, and if the frequency is close, then this frequency of changing is very slow, so you can actually hear it. All right, let me switch it off. So this is the effect of beats. I can maybe show you another simulation of how this works. Let's see. This one is, oops, just a second. Let's see what it is. Okay, so this is just a single frequency. Okay, again, I have plot some pendulum. Then I can plot, sorry, no, this one is this. I can one. Okay, what is plotted here, okay, maybe what we can see, so there's a red one and there's a blue one, and I plot two plots independently on top of each other. So they have amplitude of 1, and clearly you see that they have a different frequency. So the red one is going with some frequency, the blue one is going with some other frequency. Sometimes they agree, sometimes they do not agree, right? And the places where they meet, they are on top of each other. This is where when you add them up together, this is where they will be large. In the places where they are out of phase, they will cancel each other. So if you take two of those together, same amplitude, just slightly different frequency, you will, and you simply make a linear superposition of the two, you will get exactly the beating effect. So I just took two of those pictures before, I added them together, and you got exactly that. You have a maximum, minima, etc. And you see this overall beat frequency and the carrier, it's called carrier frequency. And this is something that, again, happens very often. There's another demonstration here. I have two tuning forks, and they have very similar frequency. So first I will show you that they are coupled. They are coupled because, I gave this guy some initial condition. It's going, then I stop it, but there is still sound because the second one picked up some energy and it took off. Of course, you don't see them, but so basically what I'm saying is that I give this energy. This one is completely stationary. Now energy is slowly moving to the other one. I stop this guy, and this guy is still going. And so the energy is being transferred by this air oscillating here. The coupling goes through the air, through the sound here, right? And they have very similar frequency, so they are nicely coupled, okay? But what we can also do, we can right? So they're both going. Do you hear any beats? Not really. In fact, if they would have exactly identical frequency, right? If they would be perfectly the same, then the difference would be 0, and there will be no beats at all. That the period of beats will be infinitely long. So it will take forever for us to hear anything. So what we can do, we can break one of them. We can, add some sort of weight. Somewhere here, there's some magic place where it works best. So what I will do is I will break this one. I will modify its frequency. That's another way to modify. I don't have to go to Jupyter to modify frequency of this one. I just add a little mass here, right? So cool. This is actually a huge effect. You can clearly see that they're going up and down, up and down, up and down, right? Because the frequency is slightly different. So now this thing is probably on, I don't know what's the period, a fraction of a second, right? Yes?
Should both of those sine and cosine terms have t's in their argument?
Of course, always, right? Yeah, they're both time dependent, yeah. This is the fast thing, and this is this time dependent modulation, yeah. All right, so where are my notes? So this is how so we were able to set up the system, put in some sort of matrix equation, kind of solved it, found two frequencies, etc. There's one additional trick which you can do to describe the motion of a coupled pendula, and that is, in a sense, mathematically force the normal modes some sort of early on. Instead of, so far when we talked about pendula, we described their motion in terms of motion of number 1, motion of number 2. It turns out we can rewrite the equation and introduce some sort of new variables which are called normal coordinates, where you simultaneously describe both of them, and kind of mix them together to have a new formula, just rewrite equation in terms of new variables. So you do change of variables. So instead of keeping track of x1 and x2 independently, you define something which I call u1, which is simply x1 plus x2. And I define u2, which is x1 minus x2. So instead of talking about x1 and x2 independently, I have a sum of them and difference. Why not, right? Two variables. I can always go back and get x1 and x2 if I want to. So if one tells me that u1 is 1 centimeter and u2 is 2 centimeters, I can always go get x1 and x2 if I want to, right? So I can do it. And it turns out that if I plug those variables in other words, I take the original equations, which are conveniently erased, and make a sum or difference, it turns out that this coupling kind of separates. So I will end up having two separate equations for this one. So for example, in general, the equation of motion would look like, so let's say I can write down m x1 plus x2 is equal to minus mg over L times x1 plus x2. Okay, this is when I add two equations. And the other equation, when I subtract them, minus x2 is equal to minus mg over L plus 2k x1 minus x2. I think that's what is coming out. So if I add and subtract the two original equations of motion, which I don't know if I have them somewhere. Anyway, you can look back. Then you end up having those cross terms drop out. And you have one which has only this coefficient, the other one which has that coefficient. And and this immediately, and it looks, if I now write it in terms of normal coordinates, then I have that m u1 double dot is equal to simply minus mg over L u1, and m u2 double dot is equal to minus mg over L plus 2k times u2. And if you look at those two equations, it turns out that they are not coupled. Each of them is, equation of a one-dimensional harmonic oscillator. The first one only depends on u1. The second one only depends on u2. And you can see the oscillating frequency with your own eyes. So no determinants needed, no matrices, no nothing. We just added and subtracted two equations, and things magically separated. All right? So sometimes, especially in case of very simple and symmetric systems, if you introduce new variables, you can simplify your life tremendously. And these are called normal variables, normal coordinates. And it turns out that you can always do that. So you can always have a linear combination of parameters for arbitrary sized coupled oscillator system, where you combine different coordinates, and you basically force the system to behave in the way in which it induces the single oscillation, single frequency. So this is a very powerful trick. But usually, for most cases, you can do that only after you have solved it, after you've found out normal modes, etc. So after you know your normal modes, then you say, haha, I can introduce normal variables and make things simpler. But at the end of the day, for complicated systems, the work is the same. But for simple systems like this one, where there is a good symmetry, you can do it much simpler. Anyway, so I think we are done for today. And on Tuesday, we'll continue with forced oscillators. All right, thank you.